Hello, this is part 3 on the section about high-order polynomials. As you recall, in the first couple of videos, we looked at how to create such a polynomial and some of the pitfalls. In fact, here's our top 4. We've talked a little bit about overfitting the data and meaningless extrapolation, and we want to look a little bit more at oscillation and how error in the data can affect our best fit polynomial. And the example we're going to use is the same one as before, where we had a data set of minimum annual salaries for Major League Baseball players from 1967 to 2017. And what we want to do is fit one polynomial to all the data that we looked at last time. So let's go back to Maple and remind ourselves of what that data looked like. Okay, so here is our polynomial in red. That's the quintic. So that fits all the original data quite nicely. And the blue is the quadratic, which is a smoothing polynomial. And so recall that the quintic was guilty of that overfitting of the data, because even though it fits the points very well, it clearly is not capturing the overall trend because we have a negative salary here and is predicting a drop in salaries, which we know did not happen. Now, in terms of the data itself within those 50 years, either polynomial does pretty good, but we could say that the overfitting of the quintic leads to some meaningless extrapolation. All right, so let's move on to our next example, and that involves, notice, a 10th degree polynomial, because overall we have 11 data points. And here they are. All right, so it looks messy, but notice it's still the same concept as before, is that we have 11 equations and 11 unknowns. And what we're trying to do is find the 11 coefficients that will satisfy those 11 equations. And Maple has found them. If you want to see how long it takes Maple to do it, again, pretty much instantaneous. And then we sub those coefficients back into our polynomial, and then we can plot it and see how it does. So here's what the plot looks like. Notice I'm plotting the extra data here, and then I'm plotting my new function, and then I'm displaying them all together. And sure enough, we get a 10th degree polynomial that goes through all data points. Now, we might immediately see some concern. Here we overshoot a little bit, but we definitely have this dip that is not reflective of reality. And we also have a negative salary here in the early years of our data set. So one question might be is, what happens if we add a couple of extra data points? How does that affect our polynomial? And that might give you a hint if you are overfitting the data. If adding a few data points dramatically changes your polynomial, then something might be going on. So what we're going to do is we're going to add 2 data points, hopefully to kind of take care of these 2 dips. And so as you'll see here in these last 2 equations is something for year 2 and something for year 48. Now, since we've added 2 data points, it means I also need to add 2 more coefficients. So I have an equal number of equations and coefficients, which means my degree of the polynomial is also going to increase by 2. So now we have a 12th degree polynomial, and once again, Maple doesn't complain. It solves it just as easily as before. And if we want to do the plot just like before, here's our new plot. And for the purposes of this particular data, this actually isn't too bad. Now, once again, it looks like we're probably going to be getting some extrapolation that's meaningless. But if you think back to our discussion about modeling the outline of a vase, if this was some sort of vase we were modeling and all we care about is the points between 0 and 50, then this actually would be just fine. However, what if instead of adding points here at 2 and 48, what if we added a few points here in the middle? So that's what we did here, is we added points at 31 and 32. Now, those are really close to the data point. We already had 30. And so we'll see what kind of an effect that has on our new polynomial. Once again, Maple solves no problem. And now notice we get a very strange picture. Now we're getting a polynomial that dips all the way down to, what is that, over a negative 20,000. And then another big dip here at the other endpoint. So this is what we mean by oscillation. And so depending on how your data points are arranged, as you get higher and higher degrees, it's possible you could get a very strange oscillation that is most likely not reflecting the true situation. In fact, if you want to zoom in on the positive numbers of the y-axis, this is the graph we get. Notice, sure enough, our 12th degree polynomial passes through all the points. It even passes through the 2 extra points right here. But the oscillation between means that even for interpolation, this polynomial is not going to work well. So that's a big concern. The other thing we talked about, another pitfall, was what if there's error in our data? And by that, as an example, what if that 32 we type in as a 33? So either we measured it wrong, we type it in wrong, or whoever collected the data somehow misreported it. So all we're off is by one value, one integer in the x value. And so let's see how that affects things. Notice the gold is the original function that we had just found, and the black is the new function. And notice just having that one data point off by one integer gives us completely different models, even though in terms of passing through the data, it still does. But we see even oscillation in different ways and still problematic. Interestingly, it's a little bit better here in the middle years, but still very different. So it just goes to show that we might be overfitting the data if that one slight change in the data is changing our model that much. And it's something to be aware of when you're reporting on sensitivity analysis in the analyze the model stage of the modeling process. So polynomials are great in certain situations, but there's a lot of things to be careful of. We can get around that with some other tools, and that's what the next section is all about. So we'll see you in the next video.